Hello? Okay. Good afternoon, ladies and gentlemen. Welcome to the last plenary session of the Asian Econometric Society meeting. After this session, we'll have a dinner session. So my job here is not hard. The first job is to introduce the speaker, Dr. Heckman. This is an easy job because everyone knows him, year 2000 Nobel Prize laureate and University of Chicago professor. This is the Fuzukawa lecture, but for the record, Dr. Heckman wanted me to announce this is a makeup of his missing 2013 presidential address of the Econometric Society. The second job of mine is to control the time. So I'm going to show Dr. Heckman, I'm going to sit there the time because the final dinner session is the most important one. So let's welcome Dr. Heckman.
Okay, I'll try to keep it brief. I'm grateful for people showing up at the last day of the last session, so I'll not try to insult you. So it is an honor to give this lecture, and I do want to argue, last year I wasn't able to come to the meeting in Singapore, and so this is really, it truly is a make-up lecture, although I made up that title, so I hope it's accepted. So what I want to talk about today is a topic that's pretty basic in terms of applied economics, but this particular paper is not really so much an applied paper as kind of a view of trying to understand how to think about instrumental variables, which are widely used in the empirical work in economics. And we've heard a couple of good lectures already here at these sessions. And I want to try to introduce a concept which I'll define, called stratification, as a way to think about organizing the way we use economics to interpret and implement instrumental variable models. And I think by using this concept of stratification, which I'll define, I can talk about a framework for organizing not just a lot of econometric estimators, although I'm going to focus primarily on a version of instrumental variables, or some extensions of what are standard results in instrumental variables. But I want to be able to incorporate in non-parametric ways restrictions of economic theory into instrumental variable analysis. So the plan of the talk is the following. I want to review, just very briefly, other approaches besides instrumental variables in creating in designing and implementing strategies for producing causal models and producing estimates of interpretable economic parameters. I want to talk about augmenting and extending the instrumental variable model with the concept of stratification. I want to define strata and link to choice theory, which I think is new. And I want to consider ways to identify and bound what I'm going to call and define as the strata estimates. And there's actually a very tight link to mixture models, for those of you familiar with those. And I want to just show a parallelism. It's not an exact parallelism, but it's very close, and there's some obvious similarities. And I also then want to consider a binary outcome example. And so I want to have a touchstone here of the local average treatment effect literature and its extensions to continuous instruments, the local instrumental variable estimator that I worked with, helped develop with Ed Vitlasil. But then I also want to tie together, and this is where the economics comes together with the econometrics, the link of many of these conditions, for example, monotonicity conditions, what I think is better called uniformity conditions, with separability, functional separability restrictions. But I want to consider not just that, because all of that's well known. I want to consider the generalization of these kinds of monotonicity restrictions to general unordered discrete choice models. There's a lot of work that's been done on the case of a binary choice, where individuals are choosing, say, between schooling and not going to school, or some choice. And some work as well, done by myself, Imbens and Angrist, 1995, in ordered choice examples, but I want to consider the general unordered choice case, which I've attacked in previous work with Ed Vitlasil, but only under the assumption of a strict discrete choice model with all the separability restrictions. I want to show how you can generalize that and present results that are somewhat comparable to what we've had in the instrumental variable literature to date for the binary and ordered choice case. And then I want to introduce a couple of ideas from the theory of binary matrices, looking at what are called lone sum matrices and their values, and establish some equivalence results for these general models. And then I want to show some examples. One turns out to be an example that applies this generalized notion of monotonicity. And then I want to conclude with a discussion that is going beyond monotonicity so that we can get at instrumental variables model interpretations where we relax the monotonicity assumption. So in order to make this self-contained and put within a structure of 50 minutes or so, what I'm going to focus on is a set of more or less a familiar treatment effect model in which I have discrete instruments. These can be extended, but there are a number of technical issues that arise in that extension, and I don't want to discuss that today, although it's implicit how to go from the discrete case to the case on the continuum. But there are some very interesting and additional issues that arise that I don't think are essential to what I'm trying to do today. So what I want to try to do is also illustrate what I think is a very important link. Sometimes in the literature, there's been a contrast made between what are called structural equation models and causal models. In fact, some authors in the evaluation literature have said, well, the causal model is really very different from a structural model. And I really want to just go back and forth between these two frameworks because they really are equivalent. And I want to show you how they're equivalent and how using that equivalence can help us think. So let me lay out, instead of just talking about the introduction, lay out a general framework here that I want to use and sort of lay out what is a very simple case, but I think an important case that helps me with the basic ideas. So what I want to consider is a world in which there are cap n sub t discrete treatment regimes. So just think about different levels of schooling, or even in an unordered case, different regions of migration, for example. And associated with it is a structural outcome equation. And here, I'm going to introduce some notation, which I'll use, some of which I'll discard, but I want to use it initially, where we have an outcome equation, y, that depends on some treatment variable, like whether you go to school or not, or whether you migrate to a particular region or not. And then two unobservables, v, which is going to play a big role in what I'm going to do. And the v is actually going to be more than just a scalar v, which appears in a lot of the literature, the traditional literature. But in the end, as you can see, it can be an infinite dimensional v, and will allow us to consider very, very general cases. And then I want to add something which helps me tie these models, these causal models to these so-called causal models to the structural literature, and avoids some technical problems about, degenerate random variables. I want to add some shock variable, which is basically going to keep random variables non-degenerate. But these epsilons, these lowercase epsilons, are going to be random variables that are independent, mutually independent, and independent of everything in sight. Well, not the outcome they're predicting, but they're going to be mutually independent across the equations. So there's an outcome equation, and then there's what I call a treatment indicator here. We can also think of as a discrete choice equation, where we essentially have that outcome t is a function of an instrument z, which will be discrete for this lecture, and there would be then some finite list of treatments that are available. So we can think of this indicator variable as the generator for a discrete choice model. And of course, they're going to be instrumental variables, and these instrumental variables will be defined over this discrete support for everything I'm going to do today. Now, in the literature, and this is an idea that goes back in the structural literature to I think the first paper on structural econometrics published by Marshak in 1944, we're going to join and talk about the dependence between this treatment indicator problem and the treatment indicator variable in the outcome equation, there's going to be V, which you can think of as the source of bias. It's a source of dependence in unobservables between the outcome equation and the choice equations. And then there are going to be counterfactual outcomes, and I'm going to use the standard notion of counterfactuals, where we think I got counterfactual outcome where I fix the value of T. So I fix the treatment, not to assign it. You can think of it being fixed by a number of different mechanisms, possibly some randomization, but this is a conceptual experiment where I fix the T, I have a value of V, and I produce a counterfactual outcome Y of T. And then there's also a counterfactual treatment. And that, again, it consists of basically T of Z, fixing Z and V. And this will give me counterfactuals. And then the observed outcome, in terms of these counterfactuals, is just the counterfactuals multiplied by the indicator variable, this kind of switching regression framework, which has been around for 50, 60 years. So that's the model that I want to talk about today, and how we can identify certain interesting parameters of that model. So the basic model that I'm going to talk about in terms of the language of causality, and this, I want to go back and forth between these languages, not to confuse, but hopefully to illuminate. I want to think about basically, this is a directed acyclic graph. It's a very common model in the Bayesian networks and Bayesian causal analysis. And I just want to introduce this notation where the circled variables are unobservables, although sometimes we can get our hands on them with proxies and so forth. And we have then that there's an instrument that's causing treatment, and there's an unobservable causing treatment, and this unobservable V is basically, possibly, this missing unobserved factor is giving some spurious dependence between treatment and the outcome. So that's the standard framework in a lot of literatures on causality, but also in structural equation models. So we know that the big problem in this literature, at least one of the big problems, has been to try to understand how we can control for the role of these unobservables, these confounding variables V. And we know that the goal, at least not the goal, but a goal of many empirical models, is to control for this V. And if we do so, then we know that the counterfactual outcomes, if one's condition on V, or get able to condition on V, then the counterfactuals are going to be independent of the treatment assignment variable. Okay. And then we know that if we could condition on V, and this is a source of a lot of literature, matching and control function and other versions, to essentially say how we can actually create the counterfactual from an observable outcome, Y, given T and V. In this case, we actually could observe V, that we could equate an empirical model with the counterfactual model. Now, of course, we don't observe V, and that's, in general, we don't observe V. Now, matching actually assumes we can measure V. And so it's not what I'm going to talk about today, but there are a lot of ways to think about how we can actually model V, and I'm not going to talk about them, but it's another approach. But what I am going to do is actually talk about a way to think about instruments where, like matching and even like randomized trials, we're going to be balancing on V between treatments and controls, but in this case, balancing in terms of strata. And again, to say what I'm not doing, but also to put it in framework, there are related ideas where you can think of measurements that may span V, or somehow we can replace V with various control function procedures, various kinds of matching on variables, either perfectly measured variables or mismeasured variables. And again, I don't want to really talk about that, but I want to distinguish from this. So this is what I'm going to talk about, and it's a version of this instrumental variable, but it's a version where I exploit the property of strata. And so here I'm just going to write down the model in standard form, where we have then, in terms of these latent variables, epsilon z, this is what's sort of giving me. So z is going to be, quote, exogenous or externally specified, but we're going to keep it degenerate, non-degenerate by putting in these shocks. So we can think of functions producing z, functions even producing v, and then the treatment variable, which I already described, and the outcome variable. And then we get these properties that this instrument is going to be statistically independent. This is what this graph is saying of v and epsilon y. But I haven't displayed the epsilons, and from now on, just to keep the graphs and the notation simple, I'm just going to keep it implicit, but they're always going to be there in case we have sets that look degenerate. We're actually going to have well-defined random variables. And here I just give a list of the standard instrumental variable assumptions. I'm going to assume finite means these epsilons that I've put up and will now take down for most of the rest of the lecture are going to be mutually independent, but they'll play a role. And we have a discrete treatment variable, and z will be discrete. That's an important simplification, but it helps explain a lot of the analysis that I'm talking about today. The confounders, of course, are the issues of z, and we have our v, and so we're trying to control for the selection bias, the relationship, the spurious relationship caused by v. And in the literature, a lot of the received literature in the IV case and the causal instruments case, whether we work with discrete instruments or continuous instruments, there's been a reliance on this property of monotonicity, which I call uniformity. The fact that across people, when we change the instrument, people move in the same direction in terms of treatment status. And that's been a kind of received approach in this literature. But what I want to do is, I will talk about that, and everything I'm going to do is going to include that, but I want to go beyond it. And so I want to consider broader frameworks. I want to introduce the concept of strata and stratification as a way to interpret and extend the range of instrumental variables. So we don't have to know V or proxy it, so it's not a matching type of estimator or control function estimator. And I want to consider a version, and the stratification approach is a version of nonparametric instrumental variables that allow us to include these monotonicity conditions, but includes more general conditions, and it helps us take the general unordered treatment choice model and allow us to consider much more general frameworks than we have before. And again, there's no restriction necessarily on the dimension of V. I mean, V can be discrete, continuous, and it can be very high dimensional. But I also want to think of using the strata matrix, which I will define, to exploit the choice structure underlying IV in any problem. So where did stratification arise? This is a concept that's been around in statistics that I'm least aware of from the time of a paper by Jamie Robbins and Sanders Greenland some 20 years ago. A more recent paper by Frangakis and Rubin some 10, 12 years ago. But what strata would be? It's an unobserved strata variable. I'm going to show how we can make it observable, or at least characterize its properties. That's a function of the unobserved confounding variables V that exploits the independent variation of instrumental variable Z, and it allows us to do a principal counterfactual analysis. So let me define what I mean by strata. So I've used the term repeatedly. Let me show it what it is. So I want to define strata. I want to array. So we think about this vector of potential outcomes. And this vector of potential outcomes would be an array of all potential treatment outcomes. And given the strata, we will get a conditional independence property that'll sound like a randomization or like a matching. We can then array. So what are the strata? So what I want to demonstrate, remember I define these hypothetical random variables where I fix the value of t and I allow it to be random in terms of it varying across people in terms of v, okay? So this is my hypothetical treatment. So we can imagine then for individuals with different v, for different values, as I keep the v going across the heterogeneous v in the population, as I as I change the instruments, and as I go across individuals, what the counterfactual outcome would be for different levels of the instrument applied to those individuals. So what I have is this matrix, and T then is going to be so this S is going to array. I'll give you an example of this, a very literal example of this in a second. But what it's going to do is just array all of the counterfactual outcome variables, potential outcome variables, for treatment status for each individual. So that's going to be the strata for different levels of the instruments, and that's why I can use this matrix notation instead of going on the continuum. And so the treatment itself can be thought of as basically just picking out some elements from S. So I have this matrix of indicator variables, which are essentially determining which instrument I have in this particular case, and then the treatment itself will be picking out some elements in that strata. So the T is a deterministic function conditional on Z and S. So the way I build up this S matrix is basically by using all the values. So the header here is a little bit unclear. It's not like I'm conditioning on Z. I'm enumerating all points of support of Z and defining the elements of this matrix T. So it's all possible outcomes for each individual in terms of choices they would take. And the key insight is that for each V in the support of V, there's going to be a unique S. So there's going to be a unique stratum associated with that V. And that's going to play a very important role. So what are the properties of these strata? The properties of the strata are that S is going to be the coarsest space. So it's going to be like a balancing score, if you know, familiar with that literature from matching. That basically, conditional on S, T is going to be a randomization. So if we can get our hands on S, it's as if we have an experiment or we have matched. So in that sense, it's like matching in the sense of balancing. But it's not matching. We have the strata, and we don't know the S in general. And you can show that this S that I've constructed is going to be the coarsest space for a given Z and for a given set of values of Z that are there in the support, in the population support of Z, and therefore fed into these causal functions, such that we can get independence. Okay, so it's going to have a property of being a kind of a minimal support, which will still give me conditional independence, a minimum space to span. So let me give you an example. So each column of this strata matrix, so let me give you an example with 3 instruments, and I'm going to carry this example much of the way, not the whole way. But basically each column is going to represent, in this strata matrix, is going to represent the value S, the values that S can take in the support, S1 through Sn. And each row is associated with an instrument. And so we can write the strata matrix as an element, AJN. That's an abstract thing, but here's an example of a strata matrix, which I think maybe will make things clear. So we have an outcome. We have essentially, say, in principle, we have a total of T sub N sub T outcomes. And so we can imagine then that we have outcomes such that in the possible strata, we have then that a person for value Z equals 1, just take the first column. This is saying that for the first value of Z1, for the second value of Z1, and for the third value of Z1, within that stratum, everybody's choosing 1. Okay? So that's why the elements are 1, 1, 1. And the second element in the strata would be the situation where, for those sets of unobservables, where we would have for Z1 equals, for Z equals 1, for Z equals 2, that we would have then that the individual will choose 1, but in the case where Z equals 3, they would switch 2. And then the final column is just where everybody switches and takes the final treatment, T sub NT. N sub T is the number of possible treatments. Okay? And so we have basically that the number of stratum points is going to be NT cubed, simply because the number of rows, that's going to be the power, right? So that's the strata matrix. So in terms of a late example, we can go to the literature and say, well, the first column here in my example, if I really had a case where I had 3 outcomes, but here I'm going to consider, say, people who always choose 1, in the language of the late literature, those would be the never takers. The compliers, if we think that higher values of Z boost T, would actually be those individuals for whom, when we set Z equals 1, they go to 1. Z equals 2, they go to 2. Z equals 3, they go to 3. And then the always takers would be those values, those people with values of V, such that for every value of the instrument that we set, they would all take 2. And we could go through, and there are actually various versions. I've already slightly extended what late does anyway. But the key idea with the stratum is if we think of a 2-dimensional V, and as I said, this can be a very high-dimensional V. When we think of a 2-dimensional V, these treatment strata, that the treatment depends only on Z within the strata, the values of Z within the strata. And within each strata, we get an exhaustive partition, and you can show that these sets are going to be connected sets, I mean generically. And that you're going to then partition all of the space into, all of the V space into these various strata. And so T is going to be a randomization within the strata. That's the kind of key idea. So from the strata, I can kind of map lots of values of V, but they're going to be kind of mutually exhaustive. So I can think about this in terms of my, and that heading here is just wrong. I don't know, I realized this about an hour ago, but it's too late. So this is just the directed acyclic graph associated with the strata matrix. So V is being fed into S, and the random variable Z is going into T. Where Z is playing a role is it's just giving me, the support of Z is helping me evaluate the functions that are the constitutive elements of S. Okay, and then we get the usual diagram. So I've just added kind of an intermediate step, but I think it's an important intermediate step. So what are the properties of strata? So if I knew S, I can identify counterfactuals within the strata. And that just follows directly from the definitions that I gave. And so I could then create counterfactuals, and I know that Z is going to be independent of YT within the stratum, and that Z is independent of S and Y of T. Okay, so that's the property of an instrument. And so I get some very, very nice properties of strata. But the problem with strata is that they're unobserved. So all of this is a nice idea. I mean, if I could observe V, I could match and I'd be home free. So why is stratification useful? What's going on? Well, if I had the strata, I could identify a bunch of treatment effects within the strata, obviously. And what I could do is then talk about the support and where are the strata being defined. The strata are being defined for those values of T, or S, sorry, that actually have positive support for some values of T, okay? And I can construct a series of counterfactual outcomes. So here's a strata set that would be associated with these different sets. So, for example, when I define this chi1 here as these partitions of this set of S, that literally I have chi1 would consist of S1 and S2. Those are the strata associated with my being having a 1 occurring. There are also strata associated with a 2. That's strata S2, so the choice 2 being, and then there's one stratum, in this case S2, where I actually have a choice 3. Okay? So as I go down the rows, I'm going across the Z's, and going across the columns, I have the strata. So this is this is just a particular example. I mean, it's an example. I could have more general strata, obviously. Could have N sub T. So let me now express this model in matrix form and talk about what the identification is and then how I can actually use these strata probabilities. So the notation in matrix form is I want to think about the probability of selection. So what do I know in the data? The first two elements, the first two rows in this table are what I know from the data. These are the propensity scores. These are the probability of choosing particular treatment status. And the Q sub ZT are the outcomes that I observe. So those are data, if you want. And what I don't know is the probability of being of various strata, the P sub S, or the strata outcomes. I mean, those are the counterfactual. Those are the ingredients. If I knew those, I could answer a lot of causal questions. And the question is, how can I go about addressing those questions? So let me set up one more piece of notation that's going to turn out to be very useful. So I gave you an example. So if you look at this example A, this matrix A, where I have 1, 1, 1, 1, 2, 3, 2, 2, 2, that was my cooked up example. Those are the possible strata. When I say I get that, say, by some restrictions. And I'll show you how to get those restrictions in a minute. But out of those, I want to generate binary matrices. And the binary matrices are going to assign 1s and 0s. And the A sub 1 is going to assign a 1 to those elements in this kind of template, if you want to call it A, where you actually have a 1. So if you look at the A1, you'll see that A1, it has a column of 1s corresponding to the A matrix just above it. And then there's a 1 in the first column, I mean in the first row of the second column, but then there are no more 1s. So that leaves me then with this matrix of all zeros, remaining matrix of zeros. So that's A1. So I'm going to take a binary matrix and select that out of A. Okay, so So I can do that with A2, and if I do this, play by the same rules, the easiest to see is A3, because if you look at A3, A3 is down here, there's only one 3, and in the corresponding place down here is A1. This is what the strata indicator is, but here's an example of what the strata indicator is. Now, why is this useful? The reason why it's useful is that we actually know AT, or at least economic theory will frequently give us restrictions on these AT matrices. So we will know these. And then we can form some very trivial but useful relationships between the data, which is on the left-hand side of this equation, and the right-hand side, which can be written as a function of those indicator matrices, those A sub t matrices, which are known. I mean, with the patterns of which were known would be imposing some restrictions, and the unknown strata probabilities. So you can see that this already is kind of suggesting how we might go about doing this. I mean, if you went to Manuel's lecture, he was using essentially, not this notion, but he was using a notion of a mixture. This looks like a mixture, and in fact it is. So the question is, if we can get some structure on the AT, we can then get some information about the strata probabilities. So just writing this in matrix notation, I can write the stratum probabilities on the left-hand side as this A sub t, this binary matrix. So the PZ of t, that probability matrix for t, the probability that a particular t is selected, given various elements of S, is going to be this AT matrix multiplied by PS. And I can array that in this matrix form. So that's the probabilities. But also the outcomes multiplied by the probability of selection, which are observed, right? These are observed data. So if you go to the left-hand side, we observe this thing. This is y given t and z. This is the probability that cap t equals t. So we observe this. This can also be written as a function of, there's a mixture of, right? This is like a discrete mixture over the counterfactual probability, just stratum conditional expectations, and the probability that you're in a stratum. And so if we just use the notation of Hadamard products, we can then simply write this thing, so it's just notation, just element-wise multiplication, but basically we can say we think the left-hand side is a function of this thing here. These are the unknowns and these are the knowns. So then, I mean, it's clear that we can identify strata. So at this point, we're in a linear algebra world. If we were in a continuum, we'd be in an operator world. And I can retrieve the unobserved strata probabilities, or at least certain functions of those strata probabilities under standard conditions. So the benefit pedagogically of looking at these discrete models is basically we get standard results in linear algebra. But basically we know that we can, if we just define this alpha bar, or if A bar, let me define one more piece of notation, where A over bar is basically just this array of these indicator matrices, and here I'm just using the example. It'd be a more general list, so I'm using my 3 example, but it's a more general theorem here, obviously, that we can identify some linear combinations of the probabilities. We know that just from linear algebra. That may not be all that helpful. That's not identifying the stratum probabilities. And we get a comparable result on the counterfactual outcomes, the counterfactual means. So then we can basically say, well, we can form the Moore-Penrose inverse of these AT plus, which is the Moore-Penrose inverse of AT, to come up with the counterfactual means associated with AT, and then the probabilities associated with P of T. So that's a standard linear algebra. But what's interesting to say, and this is where we get something that's beginning to look helpful, and that is that if we have full rank on A bar, which is basically saying, if we get full bar, which is basically saying we get the rank of A bar, is this the number of stratum elements, then the probabilities of the strata are identified. And if we knew the stratum probabilities, and that the rank of AT is of n sub s, then we can actually identify the counterfactual means. Because remember, the left-hand side, we can then identify these things here from the data that we actually have. So it's a rank condition. And again, this is just straight linear algebra on the rank conditions. And we can also do better. If we fail, then we can actually produce what we can show to be sharp bounds on essentially the probabilities. So even though we're not going to get, in many cases, the probabilities point identified, we can, using some standard calculations, compute probabilities, bounds on P sub S, and also probability bounds on the strata, okay? And then again, this is just using the Moore Penrose inverse and using information that we supply to the problem in terms of AT and A, and the various matrices formed from that. So the key identification result is that the identification depends only on the properties of the strata matrix. And I would argue this simplifies the nature of the identification here. The strata matrix governs how instrumental variables and unobservables interact to generate treatment choices. But you can also see the problem, that as we increase the number of instruments, right, the number of strata grows exponentially. And the number of observed parameters is the number of observations is like nt into the z, and the number of strata is growing. So getting the rank condition satisfied requires that we somehow restrict the number of columns in that strata. Okay. Oh boy. Okay. So the idea is then to restrict the rule. So here what we're going to do is we're going to use economic choice theory to restrict how z and v interact to generate the treatment assignment. So, and again, I just stress that right now I haven't had to put any particular structure on those f functions, other than they be functions, and I haven't had to talk about the dimensionality or the continuity or discreteness of the v. And so I guess I'm running out of time. I've just set up my notation, so maybe I can leave you with a nice notation that's maybe completely useless. Let me get through this. So I had this example, but it may be a little too elaborate. This goes back to the example I had a minute ago, where I have, suppose that the A matrix, I have some restrictions that give me the A matrix. Then you can show, you work through this example, that I can clearly, so the third row here refers to what I get from the instrument Z3, conditioning on Z equals 3. And we can take values for these strata. And in the Z3 row, we have 3 possible values, 1, 3, and 2. Just look at the bottom row of that A matrix. And you can go through a calculation, which I guess I won't be able to go through, showing that in this particular case, under these conditions, with these models, we can actually identify the stratum probability, and we could identify this particular conditional expectation, E of Y3 minus E of Y1, for the stratum S2, which is like the complier stratum. So you can get identification. I guess in the interest of brevity, I'll just have to lay at abstract levels. And all I do here is make an example of, say, this is like a mixture problem, only it's not a mixture problem, but like most mixture problems, it's got some kind of linear independence condition on the kernel of the mixture problem. And here I just make the analogy that we really are dealing with a mixing distribution on the stratum probabilities. And we want to, if we can guarantee or get properties on linear independence of these stratum matrices and these indicator matrices, we can end up identifying the counterfactual means and the counterfactual probabilities, at least on the stratum where we can actually have the support. So it's linear independence is just basically translated to full column rank on this strata matrix. So let me just give you a very simple example, and that's the standard case. And the standard case would essentially be the case where we consider all possible outcomes in a binary outcome case. So here, the only number of outcomes are 1 and 2. You can either go to school or not go to school. And so for different values, for different strata, we could essentially have for the instrument Z1, Z2, and Z3, have a cluster of people for whom, no matter what the value of Z, they never go to school. And then we have others in the second column for whom you could actually have Z going to, for Z3, they would switch status from never going to school to going to school. And then the third column, you go from a case where you have nobody going to school. With Z2, you go to school. And then with Z3, you don't go to school. This is just all possibilities. That's what the stratum matrix is doing. And it's clear in this particular example that, you know, each column represents one stratum. The number of stratums is strata is 2 to the n sub z. And so we basically have that the n sub s, that the rank of A is clearly going to be much less than 8, which is the number of strata. So to get identification, we require reduce the relevant strata. Now, how does the literature proceed? The way the literature proceeds in putting restrictions on this strata matrix is to invoke some form of monotonicity. And the monotonicity essentially is basically, in words, I'm going to have to use words, I guess, is basically saying that everybody's going to respond the same way. I mean, they don't have to be, so it's not really monotonicity in the mathematical sense, it's a condition across people. It's saying, I mean, the function could go up and down as z increases, so it doesn't have to be monotone for an individual, but it has to move uniformly, at least in the same directions across people. That imposes some restrictions. And that restriction is basically saying that that strata matrix is going to be a lower triangular matrix. And that lower triangularity actually is going to give me some invertibility criteria and will actually lead to what the standard late probabilities are. So under these monotonicity strata, we get over the relevant strata, and here the slide is a little bit unclear. The relevant strata would exclude, you get rid of the complier. So the people who move in response would be the relevant strata, not the full strata. You won't get full stratum support, but you are going to get within the columns of the stratum, and therefore something that's depending on a subset of the unobservable V, which will be defined precisely, those in those strata. We can define the strata probabilities for those and the associated counterfactual means. And we know from Wittlissel's previous work, although we can reproduce his theorem with trivial results mathematically, that under monotonicity, that this monotonicity implies, as implied by, a separable choice function. So you get this result. Okay. And so out of this pops late. So over the relevant stratum, where we can define these, we can then end up with the late estimator as essentially a solution to those particular equations that I talked about before. Okay? So you get the late effects. Now, how can we generalize this? So how much time do I have?
8.
Oh my God. So this is the interesting part. Give me 10 anyway. So no, I mean, this is all linked. So all this is kind of familiar. You say, why am I doing all this? Well, the reason why I'm doing this is this can be generalized to the general unordered case. So instead of my dealing just with a binary case, with multiple outcomes and with multiple criteria. No longer just an ordered choice model. And it gives us a way to look at preferences, choice rules. So I'm just going to have to state a bunch of results. So in some earlier work with Wittlisel, we considered the unordered discrete choice selection model and talked about how to identify certain treatment effects, and even considered how to identify average treatment effects, various marginal treatment effects under various conditions on the underlying discrete choice model. But what we can do now is actually define this without imposing the model, but it turns out essentially we are implicitly assuming such a model. And here we make a property of use some binary matrix notation. And so again, I'm just going to invoke a couple of terms which are actually useful. And that is that a binary matrix that can be uniquely recovered by its row and column sums is called a lone sum matrix. And the two matrices are, so that's going to be a lone sum matrix, and that's going to turn out to play an important role in this generalization. So there are a class of binary matrices determined only by knowing the row and the column sums. I mean, there's some problem like that in looking at Fréchet bounds, but here you can look at this more generally. So that's a lone sum matrix. And the maximal of the matrix is something with the cardinality of AT. Those are my selection matrices, AT dimensional, cardinality AT dimensional matrix, whose ith row consists basically of a bunch of ones and then followed by zeros. And the maximal element is the number of ones and zeros. And remember, the AT matrix basically just consists, all of these indicator matrices are binary matrices are ones or zeros. We're just counting number of rows, a number of ones and zeros in each row. And that's going to give me the maximal of the matrix. And I'm going to array it in this particular order at the last bullet here. So this is a key theorem. And let me just state the theorem. And there's actually, I won't have time to prove it, but there is a proof for this theorem. That for each strata matrix, we can make the following equivalence results. That for each strata matrix, T is lonesome. So if we have a lone sum strata matrix, where it's determined by the row and column elements of that AT matrix, which is given by a priori restrictions, that basically that's equivalent to saying that each strata matrix AT is equivalent to its maximal A bar of T. And it also turns out that these are equivalent conditions. That this is equivalent, this lone sum condition on the AT matrix is also equivalent to what we call generalized monotonicity. And this is kind of the obvious direction in which monotonicity can go. And that is basically saying that you can, basically when you change Z to Z prime, the people are going to move in the same direction across choices. Across V for the same choices. They're going to be uniform across people in those movements, but they don't have to be uniform across choices, and they don't have to be monotonic, actually, in terms of V. So this is kind of a generalized monotonicity. It really should be a generalized uniformity. And finally, and yet another condition is basically that this is equivalent to a generalized separability. That condition, being a lone sum matrix and having this AT maximal and equal to its maximal, and then this previous condition on generalized monotonicity is also equivalent to generalized separability, which gives us this representation here. So you can come up with a separability, and you can also come up, and this is just really an elaboration of the previous point, a random utility representation. So these are equivalent. We can think of these models, just in terms of the previous literature, we can think of these things equivalent. The new result is the characterization of the binary matrix through these lone sum properties or maximal properties, and I'll show you why they're useful. So let me just give you an example, and here's from my co-author. I forgot to mention my co-author, but he's played a pretty basic role, and he has a great example and an application, extension of these results in his thesis. There's been a lot of work on something called movement, the MTO experiment, the moving to opportunity experiment. And like a lot of the work in the literature in randomized trials, people have looked at only what are called intention to treat estimators. People randomly assign packages, they can sort among various treatments, and people then either comply or don't comply, and then they try to come to some overall causal parameter by inflating up, assuming randomized assignment within the treatment that's chosen, which is a strong assumption. So let me just give an example, and I'm not going to be able to really develop it in any detail, but just to give you the flavor of the analysis. So in this work, Pinto has a very nice application looking at movement to opportunity. Movement to opportunity randomized access to budgets. Some people were given access to vouchers, which allowed them to choose within a given set. They could move to neighborhoods close by, or they could move to neighborhoods far away from where they currently live. The idea was to see what the effect of mobility was. And so we can do a reveal preference analysis, and I'm just going to have to curtail it. But basically we can say, well, agents are picking over these choice sets that they're randomly assigned, where they go, what's optimal for them. So we can take this utility representation. And we just invoke standard reveal preference. So you know what reveal preference is, so I'm going to use reveal preference. And it turns out that in this case, this restricts the number of possible treatments. So that, and here I was going to offer an example, but I guess how many minutes do I have now? -1 or 5? Oh, it grew. Somehow it's growing. So if I go another 5 minutes, I'll get 10. But basically, so just to get the flavor of it, what you have in this experiment is randomly assigned subsidies. So some people get like subsidy 1, some people get subsidized 2, some get subsidized 3. And the subsidies are different, and and some of them broaden the choice sets that agents can have. So without going through all the details, because the notation is dense, you can go through a standard reveal preference analysis and eliminate a lot of the choices, the potential choices. That puts restriction on what I call the AT matrix. And so you can eliminate a lot of outcomes. And so these restrictions then, by just using standard reveal preference, I'm not making any functional form assumption on utility. I'm assuming people are maximizing utility. I'm assuming the kind of Samuelson type reveal preference is governing the data. But then certain budget sets and certain treatment choices can be eliminated. So certain of the possible strata are eliminated under the condition of rationality. And it turns out, in this case here, this is the set of remaining strata. But you can show that the strata matrix is lonesome, that the strata probabilities are identified within these strata, that the strata counterfactual expectations are identified, and the treatment assignment function can be represented as this random utility representation. So this interpretation plays a very powerful role. It allows us to link structural and causal models. It allows us to connect general monotonicity criteria, general separability criteria, but it also allows us to look at this A matrix, which is basically something where we have a lot of prior information. So instead of just saying we kind of hope it's monotone and we hope we satisfy some version of generalized monotonicity, we can actually look at identification by looking at the property of sort of which strata are eliminated. So we have lots of strata, but economic theory can eliminate those strata. So in this revealed preference analysis on MTO by Pinto, he eliminates quite a few. But you can go beyond monotonicity, and here's where I at least want to stake a claim and show you an example and give you an intuition. Because the key thing about the invertibility and the key thing about the identifiability over the relevant strata is that you have invertibility. And so any restrictions that give you invertibility will do so. So let me just give you another example that we've investigated. It's an example where we go beyond the standard monotonicity, which is really a statement about levels of the Z, you know, how people are ordered as I move up from Z, but not about the change of Z per se. So we can go beyond. So the key is to get your hands on these invertible A and AT matrices, or at least on the relevant strata, and then you can identify counterfactuals on the relevant strata. And so here I'm going to go through the same kind of notion here, but I want to consider an example, just an example showing what's possible. You can get a treatment indicator, so there are three possible choices. We can think of these as drugs, three possible drugs. And we think of Z as a vector. And so Z1, Z superscript 1 is going to be like the first component of Z, Z superscript T is the second, and Z superscript 3 is the third. And so the example I wanted to pursue was basically one of saying, suppose we have different advertising campaigns. And so Z sub 1 indicates the advertising for drug 1, Z sub 2 indicates advertising for drug 2, Z super 3 indicates advertising for patient for drug 3. And now I'm going to invoke a condition. And the condition is basically saying that if I find people switching from under some advertising regime, say Z, to an advertising regime Z prime, then I'm going to require that if I switched from T to T prime, that the reason why they switched, or the order, would be condition 4, which is saying that what happened was that I increased my advertising on T prime relative to T. That's why they switched. So, you know, the point is it's the increase in T prime relative to T, the amount. So if I invoke that, that's going to give you a restriction. That's going to give you the lonesome matrix property. It's going to violate monotonicity. I'm running out of time, but I'm near the end here. So the trouble is I haven't explained quite a bit of this, but this violates monotonicity. I mean, at least you can see from this final column here, looking across treatment choices, you have then a situation with the two different advertising campaigns going across the strata, say for V equals V and V equals V prime. People switch. We move going from Z to Z prime, people move from 2 to 1, and in the second column there on the right-hand side, you go from 1 to 3. But you can prove the following theorem, that a matrix, that over the relevant strata, this model is going to be identified. So let me just summarize what I talked about. So what I was talking about today was kind of supplementing the standard instrumental variable analysis and supplementing in a way using strata. And so this is what I'm doing. The adding measurements is just a typo. It's just nothing to do. It shouldn't be there. And so what we can do is, and what I've done here is looked at the instrumental variable strategy and talked about the benefit of strata, understanding how strata operate, and understanding that putting some structure on the strata, which is what economic theory does, and what essentially the late estimators are doing, and certainly you can put the ordered choice model, and I showed how you could put the unordered choice model through a version of a generalized monotonicity or generalized separability condition, which is really equivalent, that putting structure of that sort substantially reduces the number of columns in that strata matrix and gives us identifiability. And even though we might not get full identifiability across all the strata, it will give us identifiability over the thus restricted strata. And we can at least understand which set of parameters, which set of causal parameters would be identified relative to the instruments that we have, and the potential outcomes that we consider. So I argue that the stratification condition is a generalization of IV. It works like matching. It works like randomization, not by controlling for the V through the standard kind of control function method, by balancing unobservables within each stratum. It allows us to incorporate the restrictions of economic theory to bound or point identify causal effects. And this provides a more interpretable and transparent version of identification of nonparametric IV. And it has the advantage that we aren't taking a particular structure, we aren't assuming that V is somehow a single dimension. You know, they say it could be a very high dimensional object. But I think it helps us to organize thinking and gives us maybe a way to, certainly a way to think about more generally about what we get from IV, and that we can get IVs and use IVs in situations that are highly irregular from the point of view of standard monotonicity criteria and from standard choice theory. But it does allow us then to use the economics of the problem to restrict the admissible stratum. So thank you very much for your attention. I'm not too much over, so thank you very much. Questions?
Okay, let's thank Dr. Heckman for his great speech. I can understand the content of the speech is heavy, and the time constraint make it heavier. Now, finally, I would like to ask the four program coordinators to come up, and they have some announcements, and we have to thank them.
So I should get off the stage.
Yes.
No questions.
Hing Wang.
Okay, on behalf of the organizing committee, we would like to thank, everybody for your active participation. I hope, during the past 3 days, we all have learned from each other, seeing old friends and making new friends, of course. And so next year, we hope to see, everybody again in Montreal. Thank you.
I have one announcement to make. We have a bus going to the subway station. It departs from here at 6:45 in front of the building, 6:45. There's a shuttle bus going to the subway station. Thank you.